Okay, I need 2 volunteers here at the beginning while we're waiting for everybody else to come in. You have to come up here and do something. Come on up. Okay. So each of you, actually I don't want 2 people that are sitting together. So Lucas, you and Julia stay. But Rick, why don't you come up? So here, come here. Come here. So your job is to grind up, this is a spice. So you grind it up good, and then we're going to take it back and show it to the people around you. We're going to smell it, okay? See if you can, you have to really grind it like this, look. Okay. So we got 2 spices here that we need to identify. Okay, you can go back and grind them at your seat and then show it to your neighbors. Later on, I'm going to ask you whether you know what it is. Okay, so here's how we're going through the history of organic chemistry and the development of the molecular model. So generation by generation, and last time we got up to students of Kekule who actually did experiments to allow people to figure out something about structure. Not only what was connected to what, that's constitution. Remember the nature and the sequence of bonds. So we had composition, what elements are there, what ratio they're in, how many atoms, right? Then constitution, the nature of sequence and bonds. And now we're going to see if you can go beyond that without cheating and using X-ray diffraction to figure out how things are arranged in space, so structure. And we talked last time about Kerner's proof of positions in benzene and his proof that all the positions in benzene were equivalent to one another. And today we're going to go really to the next generation. Kerner wasn't all that much younger than, or he was at least halfway in the generation there. But Van 't Hoff is a full generation beyond. So we're going to look at him. It says under him tetrahedron. And it says down here, tetrahedral carbon. And also, we'll see something about Albert Ladenburg and about your, whatever, great-great chemical grandfather, Peter Kohler at Harvard. Okay, so as we were closing last time, we were looking at this definite picture of the arrangement of atoms in space, where the models are clearly real models held together by rubber tubing, and they're tetrahedral, and it explains why there can be 3 isomers of disubstituted, symmetrically disubstituted ethane. Of course, it was wrong. Do you know why it was wrong? Why they're not 3 different bottles? Yeah. Because you can rotate about the middle bond freely. It's not frozen in one rotation here, or is it? We'll see something about that later on. That turns out to be what's called conformation. Remember, that's one of the C's. But now we're in configuration, how things are attached to the tetrahedron. Okay, so after Paternó had published that, he got a letter from his former sponsor who had moved on, Adolf Lieben, Austrian, who was at this time in Italy, first in Palermo, and then at this time I think he was in northern Italy, I think in Pisa. Oh, Torino, it says up at the top. Torino, 25th of June, 1869. And you can see a translation there if you click. But anyhow, it says, "Permit me, my dear Emanuele," they corresponded like several of these people who were great friends were for a very long time. "Permit me to make an observation regarding the isomerism pointed out by you and by Cannizzaro." It's a little bit of a misleading to say by Cannizzaro. He was very cautious about this, as you know, but he introduced the paper. "Between," and he shows those 2 structures here, which look like type structures with those brackets, and you can see what's fastened on the 2 carbons is H2Cl, H2Cl, and H2Cl, H2Cl. But he wrote the CLs differently, obviously meaning to denote this difference in phase of rotation. Certainly, it's not absurd, this kind of isomerism. even without any differences among the 4 valences of carbon. Remember, one could have been straight, one crooked, and short and long, or something like that. I believe, however, that I don't err when I suppose that the same cause which keeps me from accepting it will also keep all the other chemists from doing so in a silent agreement with one another. You perhaps haven't thought that accepting this kind of isomerism crosses the Rubicon, which separates speculation that's considered legitimate about the mode of combination of atoms from speculation which is less legitimate about the position of the atoms in space. And notice here that he added as an afterthought, vero, the true position of the atoms in space, rather than just chemical position, right? In all speculations that have been made up to this time, people have always been careful never to let enter in either the relative positions in space, distances and surroundings of the atoms. This idea doesn't even enter into the speculations of Kekule about isomerism in the aromatic series. So he draws the picture of the hexagon in numbers 1 to 6. Kekule believes that chlorine 1, chlorine 2 positions is different from chlorine 1, 3 and from 1, 4, because in the first case, the 2 carbon chlorines find themselves combined with one another. But in the second case, they're separated by CH. And in the third case, they're separated by 2 CHs. And to accept this, one has no need to make hypotheses about the surroundings of the atoms. That's really weird, isn't it? He says in one case they're connected to one another, in another case there's a CH in between, in another case there are 2 CHs in between, but to talk about this you don't have to talk about the surroundings of the atoms. That doesn't make sense to us, right? But it's the difference between drawing a graph which is just a graph and drawing something that's supposed to show something in space. He goes on and says, it could be that the 2 chlorines in positions 1, 2 are in truth more distant from one another than the ones in positions 1, 4, and he draws an exclamation point there. Right. This just doesn't enter into Kekule's hypothesis. Making hypotheses about the relative positions of the atoms in space would make possible 2 isomers of dichloromethane. Even accepting the symmetry of the 4 valences, that is that all the valences of a single carbon are equal to one another, and the existence of a single isomer of methyl chloride. For example, and he draws the 2 structures here, the ones where the chlorines are far from one another and when they're near one another. But that's just the graph, right? That's not where they are in space. Okay, he added as an afterthought between the lines here, there would also result 2 isomers of ethyl chloride. Right? I repeat that I don't consider this kind of isomerism absurd, but since we have no means to know the topographic position of the atoms, while we have many to know how they are connected to one another, I consider it a bit dangerous for science. Shooting off into space in search of atoms, one risks losing the ground under his feet. Right? So be careful, former student. Greetings to Canizzaro and Kerner, Amato. I'll write soon to Compisi, your friend Adolf Lieben. Okay, so be careful. This isn't what structures are about, right? They're just graphs that show constitution. So here's Kerner, you remember, before he went south in Ghent with Kekule, and on the right of this group is Albert Ladenburg, who, once you've read what he wrote, you can sort of read into his attitude there that he was a hard guy to deal with. Okay? He thought he knew a lot, and he did know a lot, but not as much as he thought. So he published this paper the next year in 1869, or the same year that Paternó published his thing. Kekule adopts 2 hypotheses. One, the 6 hydrogen atoms of benzene are equivalent. That's what Kerner actually proved. And 2, each hydrogen atom of benzene has 2 sets of 2 others which are symmetrically arranged with respect to it. That is 1, 2 is the same as 1,6, and 1,3 is the same as 1,5, although 4 is unique with respect to 1. Okay? So there are two that are symmetrically arranged. Already several years ago, I had occasion to make Kekulé aware that his graphical formula for benzene is not adequate, right? Since here 1, 2, and 1, 6 must be inequivalent, while one could have various views about whether positions 3 and 5 are equivalent or not. Why would 1 and 2 be certainly inequivalent, 2 and 6 that is, be certainly inequivalent, but 3 and 5 might or might not? Yeah, Kate?
Because between 1 and 2 there's a double bond, and between 1 and 6 there's a single bond. But if you look at 1 and 3 and 1 and 5, they both have 1 each.
Both have a single and a double. But what about 1, 3 and 1, 5? Are they 100% equivalent?
No, because the double bonds are in different places with respect to the
Aha, because one is single-double and the other is double-single going the other way. So that might or might not be equivalent, Ladenburg says. Both conditions could, however, be fulfilled through alternative formulas, which so far as I know have not been proposed before. So here are Ladenburg's formulas. And the one in the middle, the triangular prism, actually came to be called 100 years later, or a little 70 years later, Ladenburg benzene, right? Because someone was able to synthesize that. It's also called prismane because it looks like a prism, right? And then there's this funny structure on the right. Okay, so this is 1872, and there's Van 't Hoff, who is an 18-year-old student come to Bonn to see the great Kekulé. And he writes in 1876, at the age of 24, a reply to Ladenburg. Proof that the prism formula of Ladenburg suffers from the same problem as the hexagon with fixed double bonds, removes the previously asserted superiority from the former, from the prism, and makes the original Kekulé notation not only simpler, but also the presentation with which the facts conform best. Because Kekulé had the idea that what these lines really meant was how often the bonds collide, how often the atoms collide with one another. They collide more often, he thought, when it's a double bond than when it's a single bond. So he thought that in this case, although you would draw single, double, that the number of collisions actually was the same one way and the other. So you'd draw both formulas to be in between, what we would call now resonance formulas. So anyhow, this young student, 24 years old now, says Ladenburg's off base in saying the prism is better because it has the same problem and you can't get out of it with this vibration thing. Okay, the 1, 2, 5, 6, and 3, 4 derivatives are completely similar, although differing from 4, 5, 2, 3, 6, 1. So 1, 2, 5, 6, and 3, 4 are completely similar. So here's 1, 2, 3, 6, 1, 5, 6, and 3, 4, right? And you can see that just by rotating by 120 degrees, you go from one to the next. So those, he says, are completely similar, although differing from 4, 5, 2, 3, 6, 1. Do you see how they differ? 4, 5, 2, 3, 6, 1. 4, 5, 2, 3, 6, 1. Now, are the red and the blue different or not? The reds are obviously, you just rotate and you get from one to the next. How about from a red to a blue? Can you rotate to get from one to the other? From a red to a blue? Say the ones in front. What happens if you rotate to put a red line on a blue line?
Sitting on a square face.
Sam?
Isn't it sitting on a square face instead of...
Then it's sitting on a square face instead of a triangular face. It's not the same anymore. Everybody see that? Right? This as drawn, it has a triangle on top. If you turn it 180 degrees so as to superimpose the blue in front on the red, then you no longer have a triangle on top. It's not the same thing. Van 't Hoff, 24 years old, says. What do you think Ladenburg would say about that? Well, we'll see. But Van 't Hoff goes on. He says, a 1,3 product is different according to whether A or B occupies position 1 in the, right? There's single, double, double, single when you go from A to B, okay? Exactly the same thing happens in Ladenburg's formula with the prism. An adequate consideration shows that 1 and 2 are absolutely different. So 1, and notice he puts dashed lines in. Why? Why is one bond shown dashed? It says so, right? Because it's behind, it's hidden. So he's definitely showing this in 3 dimensions. And if it's in 3 dimensions, then AB goes left to right in one and right to left in the other, and you can't superimpose them. They're not the same thing, according to Van 't Hoff. Now, what would Ladenburg say about this? He wouldn't take it lying down. He wrote back and said, Van 't Hoff finds the 2 formulas below absolutely different. How is what he wrote different from what Van 't Hoff wrote? How are Ladenburg's formulas different from Van 't Hoff's?
It's not in 3D.
Pardon me?
It's not in 3D.
It's not what?
Is it in 3D?
How do you know whether it's in 3D or not?
Well, he doesn't use dashed line.
Ah, he doesn't use the dashed line. Okay, so he says they're that Van 't Hoff finds them absolutely different. But he's just drawing constitution, what's linked to what, right? I cannot agree with him in this. Van 't Hoff is dragging something into the formulas which I, together with most chemists, expressly exclude. I refer to the arrangement in space, right? So keep that out, okay? The formula takes account of the composition, molecular weight, and mode of union of the atoms. So composition and what else? What other C? Composition, that's composition and molecular weight, he says, and the mode of union, right, which is constitution. It doesn't talk about arrangement in space. Right? If Van 't Hoff's view of space really will not tolerate the 2 formulas above to be identical, then I invite him, for his own special purposes, to use a different benzene formula which was proposed by me in the year 1869 when I compared the hexagon and the prism for the first time, together with the prism, to which it is, for me, certainly identical. It is a so-called cross of David. Even Van 't Hoff will have to find that these 2 formulas are absolutely identical. Okay, now how could the prism be identical to this? There's the prism. They certainly don't look identical, but watch this. Let's twist it. Keep all the bonds, but twist it. All right? So as long as you don't have dashed lines for 3D, they're the same. One is just twisted. Okay, so Ladenburg is expressly keeping this out. Now this point of view survived for quite a while. Here's some notes taken by a former Yale colleague, R.M. Fuas, in the 1920s when he was a student at Harvard in Kohler's course. His notes say, benzene gives 1 monosubstitution product and 3 disubstituted. Cyclohexatriene, if you had the ring with double, single, apparently requires 4 disubstitution products. So 1, 2, and 1, 6 would be different, it was argued. But then he shows another example of an experiment that's been done here with this molecule. Now these hydrogens could be, it turns out that, that those hydrogens we'll call later alpha hydrogens because they're the first next to a carbonyl group. So here's a carbon-oxygen double bond and then a C that has the H. Carbon-oxygen double bond, a C that has the H. Those are called alpha. And it was known that it's possible to easily substitute alpha carbons with other things, more easily than other carbons typically, other hydrogens. So you'd expect to get 2 possible structures. You could do this alpha one and get the R in that position, or this one and get R in that position. So you'd get two products, right? Those two. We can alkylate, that is put the R group on glutaconic acid in several ways, but we always get the same product, 1. 2 cannot be made, no matter how we go. Hence, it is not surprising that only one ortho-disubstituted product for benzene exists. The double bonds shift until the stable system is reached, right? So you can't make one, or if you make it, it immediately transforms to the other one. So there could be 2, but there aren't. Okay? So this is 40 years later, almost half a century later, and he's still saying the same thing. Okay? Now, is it really that? Well, you can calculate by Spartan that the minimum energy really is symmetrical with equal bond distances, but it vibrates. It can vibrate like this, right? In and out. And that the frequency of that is 1276 wave numbers. You've taken spectra. You've seen that kind of thing. Although this particular one is not active in the infrared. You can't see it in IR. It's called breathing. Right? Okay, but there's another way it can vibrate like this. Distort in that direction, then back to symmetrical, and in the other direction. See what that is? That's distorting in the Kekulé direction. Single, double, right? So that one is at 1367 wave numbers, the Kekulé distortion. But it's around a single minimum. So at any given time, the thing is probably vibrating. So it is single, double. But the lowest energy is all the same intermediate distance. Okay, now, might you be able to push on benzene and make it favor the Kekulé structure with alternating bond distances? Well, that's a challenge. So a chemist named J. Siegel and his colleagues synthesized this one, which you'll notice has a 4-membered ring with funny bond angles attached to one side of the benzene. That means those angles are going to be stretched and so on, so they're going to distort and make that bond different. And indeed, that bond 1,6 is a little different. But on the other side of if it made that one, let's say it's a little bit long, make it single and the neighbor's double because of the way it's being stretched, then if that propagated around the ring, single, double, the ones on the left would be different lengths. But in fact, they're the same. Right? So it doesn't happen here. So that's the kind of thing that people sometimes do to test out the limits of these kinds of theories. Okay, so we've seen the position determination, and now more about tetrahedral carbon. And to get there, we're going to step back just a bit to look at Louis Pasteur, who was in a different line of business at this time. Now, it's hard to prove that 2 samples are identical because there could always be some other test in which they appear to be different, even though everything you've done so far shows them the same. But let's take carvone as an example. Here's a sample of carvone, a bottle of carvone, and if I crack it a little bit, I can smell it. It has a very nice smell. Here, let's pass it around here. Don't spill it, obviously. Do you recognize the odor? Actually, I have another bottle too. Here, let's start this one over here. I'll start it with Catherine. So just smell that one. Don't put your nose right down in it. It's not that strong. It's very pleasant, actually. Now, this stuff is called carvone. There's a reason it's called carvone. How are you doing, Rick? You're with your grinding. Can you smell anything on it? What does it smell like?
It smells a little like, I'm not sure if I know exactly how to spice it. It's a little like sesame seeds, but not
A little like sesame seeds, but
sesame.
there's another. Pass it to Shai next to you here. Let him smell. Is it familiar? How about anybody? How about the bottle here coming? Do you notice it? Is it a familiar scent?
Smells like peppermint.
It's spearmint, not peppermint, but you're close. Shai, how are you doing? Does it smell like peppermint to you?
I couldn't say what kind of mint it smells like, but it smells
Like mint. Okay, how are you doing, Yunju? You're grinding up a different stuff. You're grinding dill seed, in fact. Does it smell?
Yes, it does. They said aniseed.
What does it smell like?
Kind of
Dill seed, maybe, right? But carvone comes from that. This is a familiar scent. I'm surprised you didn't get it, Shai. And did anybody else recognize? Did you get it, Andrew? No. How about the bottle that's coming along the back row there? That little bottle. Yeah. Notice it?
Rye.
It's rye. Rye bread has that. It's caraway. Those seeds are caraway. And caraway is carve is the Latin root for it. It's like caraway, right? So carvone, this substance we're passing around, carvone, caraway, okay? Now, so let's look at suppose we took these two bottles and you distilled them, found the boiling point. Both bottles have 230 to 231, right? The densities are exactly the same. The refractive indices for those two bottles, how much they bend light when it goes through, exactly the same. The infrared spectrum are identical to the extent that any IR spectra are identical. You know from experiment that if you put more in one sample than in another, they don't look the same, right? Did you notice that in lab? If you ground up more stuff and less stuff, the spectra don't really look the same, but then you can find there is a peak-to-peak correspondence. The intensities are never going to be exactly the same. But to the extent IR spectra could be the same, these are the same. If you take their NMR spectra, they're the same. So they must be the same. Or is there any property in which they differ? Any property that those two bottles differ in? The smell is different. Now, those bottles, if they're in dark bottles, right, to protect them from light, but if I poured them out, they should be colorless liquids, but I bet anything they're brown, right, because they've sat around and a little bit is oxidized. So it's very difficult with scent because little bits of other things can make them smell a little different, right? You don't need much stuff for scent of the proper thing. So it's hard to be confident that this difference, that one of them is rye bread, caraway, and the other is spearmint. It's hard to be sure that that's a difference. But it turns out there's another property you can measure too. And caro syrup has that property. And I'm going to show it to you. It's the ability to rotate polarized light. Now, I forgot to bring my Polaroids. So what I'm going to do is ask a TA to go back to my office. And on the table in my office, there's a brown package about that big that has 2 sheets of Polaroid in it. There's the key.
Okay.
Yeah, it's not here. Sorry. Let me think a second what we can go on to. I'll tell you the measure of this, which is you have light that's polarized. Have you all dealt with polarized lights? You probably have polarized sunglasses, you know, and you can turn it and see different light reflecting off things. Have you done that? Okay, and that's why you have polarized sunglasses, because light that reflects doesn't go through the particular direction that's in the sunglasses. So you get rid of reflected light. Okay, so, but what you measure is, when light goes through a Polaroid filter, it's as if you were shaking a rope and it was going through a picket fence. It can vibrate one way, but it can't vibrate the other way. What vibrates in light? What is vibrating? What's light? We went through this before. Electromagnetic radiation. What's vibrating? The electric field. And it's set up so one of these, if you have a Polaroid filter, gets absorbed and the other one comes through. Okay, so light that comes through is vibrating this way. And if you put another one that's crossed with it like this, what do you get? What do you see? Nothing, because the first one stops one and the second one stops the other one. If you turn it like this, then it goes on through, okay? But suppose that you put something in the middle that rotated the plane of polarization so the light's vibrating like this, suppose it's going like this, right? Suppose by the time it gets to the second filter, it's like this, right? Now you have the second one like this. What do you see? Light comes right on through because that's the way it's vibrating now. If you rotated the plane of polarization, okay? That's what rotation means. Okay, now, you measure this property of a substance and call it specific rotation, which is how many degrees it rotates, and you have to say what light rotates. So the units of alpha are degrees, how many degrees it changes, per gram per milliliter. If you put more stuff in, then you get a bigger effect, right? So it depends on the concentration. So how many degrees per mole, you might say, okay? But then it's per decimeter, because the longer path you go, if it's rotating, the further you go, the further it twists. So the old style cells were, oops, no, that's not it. Nice try. This is really embarrassing. It's an envelope. Did you see it? Okay, good. Okay, let me show you the other things I'm going to show you. Okay, we'll do a trick. Here are models of Carvone. Okay, now I'm going to give them to you guys. And I want you to compare and see if they're the same. Stand up and let people see what. So decide how you, start maybe at the top with a methyl group. Each of you, both of you turn and face the thing so they can see. Now start with a methyl group at top. It starts with a methyl group. Now Russell, you describe it and then check and see whether, Eric, you check and see whether your model is the same as Russell's, okay? Well, while you're doing that, I'll go help find the thing. So tell me when I get back.
Another methyl something up here. Then we have this pointing this way.
Yeah, mine's pointing out.
Are they the same?
One of them's pointing out right here, where the other one points.
So is that real, you think? Is that just a peculiarity of the models, or does that relate to molecules?
I think it relates since they smell.
Okay, well, anyhow, if I catch my breath, these are Polaroid sheets. So here you see me, and here you don't. Okay? Now, let's see a case of rotation. So here you see crystals. And I'll put this, I'll get light coming through. And there's the Polaroid filter. And here's another Polaroid filter. Right, so I turn it 90 degrees. And now let me put the crystals in there. Now, so there, most of it's coming through. But now watch. What do you notice? What's happening? What's surprising about this? Obviously, they're rotating the plane of polarization, right? So that I have to set a different angle in order to stop the light. But what's special about this set of crystals? Some are right-handed and some are left-handed, right? That's sodium chlorate. That's the stuff that Gay-Lussac used, right? So this property was discovered of crystals early in the century. Now, how about liquids? Will liquids do it? Well, here's glass. Glass doesn't do anything special, right? It's just like the air around it. But let me pour water in here and see if water does the trick. Nothing special, right? So let's try Caro syrup. It's not quite January, but it takes a little while. It's a little bit yellow. It's sat around a while. What's happening? Well, there's an underlying yellow that biases this. But we can get different colors. So different colors of the spectrum are being blocked out. How can that be? For different angles, different colors. So the Caro syrup is rotating the polarization, but it's rotating different colors, different amounts, right? So we block off different colors at different angles. Okay, so if we're going to make a measurement of the angle, how much it rotates, we're going to have to say what color we're talking about. And that's what the D is. The D is the color. There's a so-called D line of sodium, a yellow color. The yellow street lights are that color, right? So that's the color that was used because it was easy to generate in the old times. And 20 is how many degrees, because it's different for different temperatures. Okay, so you can measure the specific rotation of a sample. And if it's in a solvent, you have to say what solvent it is because it can vary with solvent. So anyhow, back to our comparison, these odors were the same, but we might not believe it. But if we measure the specific rotation, it's equal and opposite. One is plus 62 degrees, and the other is minus 62 degrees. So these things somehow are mirror images of one another. Now here is what you've already seen. You can write the structure of carbone, either longhand or shorthand. And there are the two models, and you correctly identified a difference between them, that one has a hydrogen pointing backwards and the other coming out toward you. And is this difference real? Of course, there were differences in the sausage formulas too, but those weren't real. Remember, those two compounds turned out to be the same compound. The question is this difference real? Are there two carbones, but with different impurities in them, so they smell different, or is there just one? Pardon me, vice versa from what I said there. Okay, so tartaric acid turns out to be the same thing. Remember, Berzelius coined the name isomer to talk about tartaric acid and racemic acid, which both came from as byproducts of the wine industry and had very, very different melting points. So obviously they're quite different from one another. And one of them turns out to rotate light if you'd make an experiment like this. It rotates light to the right by 13 degrees per gram per milliliter per decimeter. Okay, but if you heat it, you get another compound called pyrotartaric acid, or sometimes mesotartaric acid. Meso doesn't mean anything except between. Do you know any cases where meso means between? Mesopotamia means between the Tigris and the Euphrates River, right? So it just means in between. So there was another one in between tartaric and racemic acid. It wasn't between in melting point. It had 140 degrees as its melting point, and it didn't rotate light either. So there were these three different forms of tartaric acid, but all were found to have the same constitutional formula, the same things linked to the carbons. So here's a problem with the model in terms of isomer numbers. Okay? Sometimes too many isomers are predicted, like Paternó's dibromoethane. He had different phases of rotation, said those were different. In fact, they weren't different. It was just experimental errors of someone who thought they were different. So sometimes the model predicts too many isomers. But often, or sometimes at least, it predicts too few, as in the case of maleic and fumaric acid, where you have a double bond. They're two different substances with different melting points and properties. With lactic acid, remember that Scheele had found lactic acid from milk, but Liebig had found it from meat, and they were the same. It was found at about this time by a guy named Wislicenus. They had the same constitution, but one rotated to the right and the other rotated to the left. There was tartaric and racemic acid, which was even more complicated because there was also mesotartaric and also what came to be called L-tartaric acid, and that was the discovery of Pasteur. So in 1848, which was another revolutionary time in France, Pasteur was 26 years old and was becoming an interdisciplinary scientist, chemistry, physics, crystallography, all he was studying. And he wrote a paper called On the Relations That Can Exist Among Crystalline Form, so crystallography, chemical composition, chemistry, and the direction of rotatory polarization. That is the stuff we're talking about, which is physics. Now, remember we talked about Mitscherlich and the ability to measure angles on crystals and distinguish crystals by their angles. So these are pictures that Pasteur was using to draw of his salts of tartaric acid. In particular, sodium, it's a diacid, so you can have different cations. Sodium ammonium tartrate is this one. And there's his picture that he drew of it. And he said, mostly you see the faces that are shown in that picture, but sometimes you can see other little faces, right? And you notice that the crystals have symmetry. They have a horizontal plane of symmetry and also a vertical plane of symmetry, right? So if you can see one of those edges, you should see the others that are related by symmetry this direction, and also symmetry this direction. So you should see all 8 in the tartrate. But always only 4 of them are observed in sodium ammonium tartrate, not all 8. Mitscherlich had studied this stuff, and he was sort of the father of measuring angles like this. But when Pasteur was trying to learn the technique and repeat it, he noticed that you don't very often get these edges all together, these little tiny ones. It usually looks like the original picture did. But when those sharp edges are truncated by little additional faces, you only see 4, you don't see all 8. So Mitscherlich had reported that that was tartrate, right? Now, they had the idea that racemate, which remember didn't rotate light, Pasteur's idea was that molecules were twisted in a right-hand or a left-handed helix, and therefore they had this effect on light to make it twist, right? But ones that aren't twisted, like racemic acid, where the molecules aren't twisted, then at least in those you should see all 8, because you will have mirror images, okay? So he thought untwisted molecules would be what's called holohedral, that is, have all their faces. So he studied the sodium ammonium racemate and was quite surprised to find that sometimes he saw the red ones, sometimes he saw the green ones, but never on the same crystal. Some crystals were right, red, and some were left, green. So he separated those crystals, the right ones from the left ones. He wrote, I carefully separated the right from the left crystals, and observing their dissolution separately with Monsieur Biot's polarization apparatus, the thing that measures the rotation, I saw with surprise and delight that the right crystals deviated the plane of polarization to the right and the left to the left. So why did racemic acid not rotate light? Because it was a 50-50 mixture of things that would rotate it one way. It's not that it was untwisted. It was that some of them would rotate it one way and some would rotate it the other, and they'd cancel out. Okay, whoops, I improved this and forgot to take that one out, sorry. Okay, so now he knows what's going on. That racemic acid is actually a 50-50 mixture of right-handed dextro-tartaric acid, D, that has a plus rotation, and left-handed tartaric acid, L, levo, which has a minus rotation, but the same melting point, the same rotation, but opposite in direction. So those are mirror images of one another. Now, and the racemic acid is a 50-50 mixture. Now this was 1848, so that's a long time from where we've gotten to, right? That was 10 years before the idea of bonds, okay? So that was resolution, the separation of a mixture into the two components, right? But what is mesotartaric acid? Why doesn't it rotate? So now we go forward 24 years to Bonn, and there's Van 't Hoff studying with Kekule at the age of 20. So that's a quarter of a century. That's a long time, right? It's longer than you've lived. So here's Van 't Hoff. He had some opinion of himself. He won the first Nobel Prize. I mean, he had a high opinion that was completely justified. In 1901, the first Nobel Prize in chemistry, and he didn't get it for this, which he should have gotten it for. He got it for inventing physical chemistry. The most admired trait he had was imagination. So he liked poets and artists. In fact, his hero was Lord Byron. Look at that. Okay. And in 1874, as we said, he was a student. And he wrote this, a pamphlet in Dutch, which was then translated into German and called The Arrangement of Atoms in Space, and was published in 1877. It was 53 pages long and heavily illustrated. And look at the website for this. One of the wikis I've assigned is that website. And also this website about criticism of Van 't Hoff by a guy named Colby. So here's Hermann Colby. He was more than twice Van 't Hoff's age, and a pillar of traditional chemistry. He wrote in a review of this book, it is completely impossible to criticize this booklet in any detail because the fancy trifles in it are totally devoid of any factual reality and are completely incomprehensible to any clear-minded researcher. The brochure begins with the words, the modern chemical theory has two weak points. It says nothing either about the relative position or the motion of the atoms within the molecules. This is absurd, right? But he was wrong, right? Now, am I like Kekule, because I'm more than twice as old as you are, right? So those are 3 websites you should read about this. But in fact, it's not true that Van 't Hoff was devoid of any factual reality, because we've already seen some of his evidence, and we'll see more next time.